Let's talk about generators and relations for symmetric groups. We've already done an instance of this in the previous problem session when we looked at the symmetric group S3. Okay, and recall, we said that there exists a surjective homomorphism from the free group on two generators to S3. Okay, we constructed such a map. Now, how did we define this map? Let's call this map pi. It was given by the following. You map the generator A to the transposition 1, 2 and B to the transposition 2, 3. Mapped it to the two simple transpositions. And if you specify the values on A and B, that's enough to give you a group homomorphism from the corresponding free group. That's by the universal property of the free group. Okay, we said a few things about pi. So, pi is an onto map, it's surjective. Why is that? Because 1, 2 and 2, 3 together generate the group S3. That's one. Now, what we want to do really when we say generators and relations, so the word relations is really something to do with the kernel of pi. So, what we want to do is to understand what the kernel of this homomorphism looks like. Okay. Now, there are some obvious elements in the kernel which we can immediately write down. So, let me give you a few elements of the kernel. Before that, recall that the kernel, well, what is it? It's certainly a normal subgroup of, this is a normal subgroup, as we know, of the free group. So, let me just abbreviate the free group to F now. So, this is property 1, the kernel, and here are some elements in the kernel. So, observe that the element 1, 2, the transposition, has square identity. Okay. So, if I similarly look at the square of this word A, in other words, let me look at the word A occurring twice, and recall that elements of the free group are all equivalence classes of words. So, I look at the word AA, and if I compute what its image under pi is, then here's what I will observe. Pi of AA is nothing but pi of A, because pi is a homomorphism, and this is just 1, 2 times 1, 2, the square of this, and that's just the identity. So, let me write ID for the identity element of the group S3. Now, similarly, more or less by a similar calculation, I also take the word BB and observe that its image under pi is also going to be the identity. Okay, so what does this mean? It means that I know some elements of the kernel. The word AA is in the kernel, the word BB is in the kernel. Okay, these are both elements of the kernel of pi. In fact, there is yet another word which now involves both A and B, which we can write down. So, I will leave space for that. So, what's that? Well, let's look at the product of the two. So, suppose I take a word AB, which is the product of the words A and B, and I compute the image of that under pi. It's pi A, pi B. That's the product 1, 2, 2, 3, which is the 3 cycle 1, 2, 3 in S3. And we know that 3 cycles have order 3. If you raise it to the power 3, then it just gives you the identity. So, what this means is, so observe 1, 2, 3 being a 3 cycle, if I cube it, I get the identity. So, in particular, it means if I compute the image of pi under the cube of this word. So, I take AB whole cubed. What is AB whole cubed? That's just the word AB, AB, AB. So, I just repeat AB thrice. So, if I compute this, then that's going to be the identity again. Okay. So, what that means is that I can write out another word. So, this is just AB, 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 and these 3 words certainly belong to the kernel of this homomorphism pi. Okay. Now, what we are going to claim is that in some sense these are these are the three words that you need. These are all the words that you need. Okay, so here's the proposition. The kernel of pi is just the normal subgroup generated by these three words. It's the normal subgroup of the free group generated by these three words, okay, which is AA. So, generated by the set containing these three words. Okay, so what is the terminology normal subgroup generated by something mean? That just means you take the smallest normal subgroup of the ambient group which contains the given subset. So, this is just sort of the obvious definition. So, definition, given a subset of a group, given a subset T of a group G, the normal subgroup generated by T is just the intersection of all normal subgroups. So, let us call it n prime. What is n prime? N prime is a normal subgroup of G which contains the given set T. Okay. And it's an easy exercise to check that when you intersect an arbitrary collection of normal subgroups, the answer is still a normal subgroup. Okay. Arbitrary intersections of normal subgroups is a normal subgroup again. And so, the intersection of all normal subgroups which contain a given set is necessarily a normal subgroup, and that's called the normal subgroup generated by the given set T. Okay. So, in our case, so let's come back to our situation. So, we said take the set comprising AA, AB and AB whole cubed. So, it's sort of cumbersome to keep writing this again and again. So, I will just call this word A square, B square. So, just mild abuse of notation here, and I will call this AB whole cubed is just the word AB, AB, AB. So, I am dropping the sort of the square brackets for the equivalence classes. Okay. So, I claim that, so let N be the normal subgroup generated by these three elements, by A square, B square and AB whole cubed. And I claim, so we need to prove really, which is the proposition. To prove the proposition, what I am claiming is that N is exactly the kernel of pi. Okay. So, recall that is the proposition. The kernel is exactly the normal subgroup generated by these three elements. So, let me give the normal subgroup generated by these three elements a name. I am calling it N, and I am going to show that N is the same as kernel of pi. Now, what we know, so let us prove the claim. What we have just said, so we know the following, that the kernel contains N. We know the following, we know that the kernel contains N, right, because the three elements which generate N are all in the kernel, and the kernel is a normal subgroup. So, N is the smallest normal subgroup containing those three guys. It's the intersection of all the normals, and so in particular N has to be contained inside the kernel of pi. So, that's the first thing we know. There's another thing we know. We know that the free group modulo the kernel, the quotient group, by the first isomorphism theorem for groups or the fundamental theorem of group homomorphisms, says that this is in fact homomorphic, or rather isomorphic to the image of this map, okay, to the image of the map from F to S3. So, I have an isomorphism, and recall what does this isomorphism do? If I take an element G in F and I look at the coset G kernel pi, right? The coset of G is just mapped to pi of G. That's what this map does. Okay? That is the isomorphism that comes from the given map pi. So maybe I'll call this map pi bar, which is just induced by pi. Okay, so I know that this is an isomorphism. So pi bar is an isomorphism of groups. Okay, it's an isomorphism. Now let's look at n now. So let's look at f by n. Let's look at the quotient f by n. I claim that since n is contained inside the kernel of pi, there is actually a map from f by n to f by the kernel. Okay, and this is in fact a surjective map. So we usually indicate it by this double arrow here. What is this map? So this is again a general fact. So maybe we'll write this down here separately. Here's a general fact which works for all groups and normal subgroups and so on. So suppose I have two normal subgroups. Suppose I have n1 contained inside n2. Okay, they are both normal subgroups of a given group G. So let's say n1 and n2 are both normal. Then I can talk about the two quotient groups. So there is this group G mod n1 and there is the group G modulo n2, G by n2. And what I have is a map. There always exists a map from G by n1 to G by n2, a surjective map. Okay, so we'll call this psi maybe. And what does this map to? Well, the most obvious thing takes the coset of G with respect to n1, the left coset, to the left coset G n2. Okay, so this is the obvious thing to do, and here's a simple exercise. Check that psi is in fact a homomorphism of groups that it is onto, and in fact its kernel, the kernel of this map is exactly, well, what is it? It's everything which maps to the identity coset. So that's going to be all elements, the cosets of elements from n2. So this is usually what we call n2 by n1. Okay, so n2 by n1 just means I take all cosets G n1 where G comes from n2. Okay, so it's sort of a short aside on homomorphisms between such quotient groups. Now our situation is similar. We have in fact f by n and f by kernel pi. N is contained in the kernel, and so actually I have a map from f by n, that's a coset of n, maps to the coset G kernel pi, which in turn maps isomorphically to S3 under the map pi bar. Okay, so G kernel pi goes to pi G. Okay, great. So I have, through this I have managed to get a sequence, I have managed to get a homomorphism from f by n which surjects onto S3. Let's call this psi. So in effect, let's just give the whole thing a name. So this map now, which goes from f by n to S3, so this is just pi bar composition with psi, is a surjective homomorphism. Okay. Now what we are trying to prove really is that n and the kernel of pi are the same, and if that were true, then of course you can see that this map psi would just be sort of like the identity map between them, and this composition here would just be the same as the original map pi bar. Okay. Now so what I claim is the following. So let's prove this as follows. We claim that this group f by n that we don't know much about at this point is in fact a finite group and has at most 3 factorial elements, or at most 6 elements. So 6 is 3 factorial in this case, which is the number of elements in S3. I claim f by n has at most 6 elements. We'll prove this in just a second, but observe that if we assume that the claim is proved, then it automatically shows that n and kernel pi are equal. Okay, so for the moment, assuming the claim, let's see what we can deduce. So observe, because f by n surjects onto S3, f by n must have at least 6 elements, right? Because I have an onto map which sort of goes down to a set of 6 elements, then the other set on the other side should have at least those many elements. Right? Just a property of onto maps. And on the other hand, the claim says that this has at most 6 elements. So assuming the claim, observe, we would conclude that f by n in fact has exactly 6 elements, okay, because the onto-ness gives you the other inequality. And what does this mean? This in turn would imply that this map that we have constructed, pi bar composition psi, is in fact an isomorphism, because it's both one-to-one and onto now. It's an isomorphism of groups. Now, if that is an isomorphism of groups, then the only option, I mean pi bar was already an isomorphism, the only option is that psi is also an isomorphism. So psi is also an isomorphism. Okay, and what would that imply? That means in particular that psi is a one-to-one map. Psi was already onto, claim is psi is one-to-one. Now observe, we sort of know what the kernel of psi looks like. Kernel of psi is just a quotient n2 by n1. In this case, it is just kernel pi by n. Okay, so in our case, what would we get? We would get therefore that kernel of pi, which is known to be kernel of psi, which is n2 by n1, which in this case is kernel pi by n, is just the trivial group. Okay, the kernel pi just has only the identity. That's exactly what we want to prove. Okay, and so we are done. So the proof is done. So assuming the claim, we are done. So all we need to do really is to prove this claim that this group f by n has at most 6 elements. Okay, and that's really where the heart of the proof is. And for a start, we should observe that this is a very surprising fact on the face of it, because what are the elements of f itself? Well, the elements of f look like this. They are all words, the equivalence classes of words. And now we are saying, let's look at the cosets of, you take all possible words in f and look at their cosets, left cosets with n, and this collection is finite, has at most 6 elements. Okay, but observe the number of words themselves is infinite. Right? Recall, if I write words, I mean, what are the elements of the free group? Words in A prime, B prime. There's an infinite number of words I can write. But somehow when you take cosets with n, then this reduces to just a finite number. Okay, so that's somehow the point. So let's try this. Let's see how this finiteness would come about. Well, it comes about because many different cosets should end up giving you the same answer. So I'm looking at all so this is my f by n. I claim that many cosets give me the same, many w's give me the same coset. Okay, for example, so let's see an instance of this. So let's look at the word a, and let's look at its sort of the inverse word, which is a prime. I claim a and a prime are actually in the same coset modulo n. Okay, why is this? Well, let's prove this. How does one prove two things are in the same coset? You just look at a prime inverse. So you push this a prime over to the other side. A prime inverse times a. So you compute what this is. Well, a prime inverse, recall, a prime was, that word was the inverse of a in fact. So this is a again. So this is just a times a. So that's just the word a square or aa. And recall, because of the definition of n, aa is in fact an element of n. Okay, so this means exactly that these two cosets are equal, that a prime inverse a belongs to n. Similarly, the same thing holds for b. Same proof, bn is the same as b prime n. So these are two examples of different words which give you the same coset. And in fact, here's the general fact again. General fact about cosets of normal subgroups in groups. So suppose I have n, which is a normal subgroup of G, and suppose I have two different elements which have the same coset, and suppose if x and y are two elements of the group which have the same coset modulo n, then in fact, I can do the following. I can hit x on the left and on the right by some two group elements that will have the same coset as g1y, g2n for all g1 and g2 in my group G. Okay, again proof is very simple. Let's prove this very quickly. Proof, what's given is the following, that x and y are in the same coset, which means that x inverse y belongs to n. This is what's given. And what is it that we want to prove? That if I take g1x, g2 inverse g1y, g2, I need to prove that this is also an element of n. Okay, so we just compute. So let's see, what would you get? This equals g2 inverse x inverse y g2. Of course, the g1 inverse and g cancel each other off, so I can get rid of them. Now what's left is just g2 inverse x inverse y g2. And observe, x inverse y was already in n, that's the given data, and this is just a conjugate of that. Okay, because n is a normal subgroup, when you conjugate an element from n, it's again in n. So this is obviously in n. So we are done. Okay, so this little general fact is very useful. It says that once I know, when two elements are representatives of the same coset, then hitting stuff on the left and the right will again produce two representatives of the same coset. Okay, so now let's look at how that's going to be used in our case. So I have a and a prime have the same coset. So what that means is, if I hit a on the left by any word and on the right by some word, that is in the same coset as the corresponding operation to a prime. Okay, so here's our corollary to our instance, to our situation. So I take a word a, another word, its coset is the same as word a prime word n, and this is true for all words w1, w2. Okay, so maybe I should really put the equivalence classes here. But what does this mean? This just says that if I take any word, so what this means is, suppose I have a word here which looks like this. There's a bunch of letters, there's an a in it, and there's another bunch of letters. Then the coset of this word is going to be the same as, well, I take these letters, keep these letters the same as they are here, replace just the a with an a prime, okay, and then keep these letters the same. So you make only one change, which is a changes to a prime. Then these two are in the same coset. These two words are going to be in the same coset. Okay, so again I'm going to drop those square brackets on the two sides. Okay, so you can replace an a with an a prime in a word, and that doesn't change the that still gives you two things with the same coset. Okay, similarly same thing for b and b prime. Okay, if I change b with b prime, then it just gives me another representative of the same coset. Okay, so that's the first observation, that you can change a's and b's, a primes and b primes to a's and b's without changing the cosets. So it's sort of enough, therefore, to since I'm trying to understand this, I just want to know what are all the different, how many different cosets can I get when I take different words w here. Okay, well, the thing is, it's enough to restrict to words w which contains only a's and b's. Okay, let's throw out the a primes and b primes because of this fact here. Okay, so it's enough to say, let's look at cosets of words which only involve a and b. Okay, so such cosets must be the same as the collection of all cosets. Okay, now how many such cosets are there? So we need a few more reductions now. So here's reduction number 3, which says, if this word, so I'm now, remember, w is a word only with a's and b's. If w contains two successive a's or two successive b's, two successive a's or b's, then I can delete those two. Then that can be deleted without changing the coset of W, can be deleted. Okay, in other words, more formally, if W looks like word W1, AA, W2, then the coset of W is the same as the coset of W1, W2, as I have deleted the A's from it. Hey, why is this? Well, it's again an instance of the same general principle that I talked about. Proof. Recall A square, which is AA, is the same as, so in fact, AAN is the same as just the empty word N, okay, because AA is an element of N to begin with. So AA and the empty word both have the same coset, which means I can hit stuff on the left and the right and I will still get things in the same coset, okay, which implies, well, exactly this fact that W1 AA W2 and W1 empty word W2 have the same coset. Okay, same thing with B's instead of A's. So this is the next reduction principle. It says you can throw out two consecutive occurrences of A's or B's without changing the coset of your word. Okay, so now that's the important reduction. So now let's try and list out all the different possible cosets. So I'm going to try and list all cosets of the form Wn. Okay, and where I will use my various reduction rules. I won't list cosets which are, which can be obtained using different representatives. So here are my different cosets. So number one, I can just take the coset of n, the coset n itself, that's empty word n. Then I can look at the coset an. I can look at the coset of b, bn. So remember, I have to look at all possible W's which involve A's and B's, which don't have two consecutive A's or two consecutive B's. Now the next possibility therefore becomes ABN, 5 BAN, 6. So now I look at words of length 3, can look at ABAN, 7 is BABN. Now I look at words of length 4 and 5 and so on. So I'm taking care not to have two successive A's or two successive B's. That's it. Okay, so here's a list. It still looks like an infinite list, but here again comes the next reduction step. We claim that these two are actually equal to each other. These two cosets are in fact equal. Okay, so that's the next observation. Claim the coset ABAN is the same as the coset BABN. Okay, again proof. What do we need to do? We need to take one of them to the other side as inverse. So look at BAB inverse ABAN, and we need to simplify this. So remember, BAB inverse is what? B inverse, A inverse, B inverse, ABAN. Inverses, remember, are the same as primes, B prime, A prime, B prime, A, B, A, N. Now, we have already proved the following, that whenever you see primes in a word, you can replace the primes by the unprimed alphabet, and that still gives you the same coset. So this element here has okay, so this is now BA, BA, BAN. Okay, now look at this word here, BA, BA, BA. That's, well, what is BA, BA, BA? That's just the word BA cubed. Okay, so I claim that this word BA cube is actually in N, but observe that the word BA cube is actually in N. Okay, how do we see this? So recall N had AB cubed and not BA cubed, but that's not too hard to change this to the other. So let's look at BA cubed inverse. Okay, so what is BA cubed inverse? It's now going to be instead of BA, BA, BA inverse, so it ends with an A, it will now be, so what is this? BA, BA, BA inverse. So I just have to write it out in the other order. So that's going to be A inverse B inverse, A inverse, B inverse, A inverse, B inverse. But then recall I can change all the primes to the unprimed alphabets without changing the n. So this, I have to put n's everywhere. So look at BA cubed n, it's the same as this, it's the same as this, which is the same as this, but then AB whole cubed is already in n, so this is just the same as. Okay, so what this means is that BA whole cubed is, BA whole cubed n, so I've shown BA whole cubed inverse n is n, so of course that means that BA whole cubed inverse is in n. But then if an element is in n, n is a subgroup, of course if the inverse is in n, the original element is also in n. Okay, so what this means is, so this proves what we set out to prove, that the word 7 or the coset 7 is actually the same as the coset 6. Okay, so you don't actually get the 7th guy in this list, and well, what we now show is that you will not get the 8th guy or the 9th guy or the 10th guy. Every other word that we would have potentially written down will turn out to coincide with one of the first 6 words, okay, or with one of the first 6 cosets. So that's going to be our next observation or fact or proposition. Claim if W is a word in AB, W is a word in A and B without 2 successive A's or B's, without 2 successive A's or B's, then the coset Wn, so let's forget the brackets now, that Wn coincides or equals one of the cosets 1 through 6. In other words, this list here, empty AN, BN, ABN, BAN or ABAN. Okay, so we have already proved this for words whose length is at most 3, right, because those are exactly the first 7 guys that I've written here, and 7 turns out to give me the same answer as 6. Okay, but what if my words were longer? So in some sense we just have to prove this by induction. So to get a sense of the proof, you should probably just work out the next few cases, but this proof is really by induction on the length of this word, induction on the length of this word W. So observe that, so I proved it already for length equals 1, 2, 3, we are done. Now if length is at least 4, suppose the length of W looks, if W has length at least 4, then what does W look like? Well, remember it's a word with A's and B's, no successive A's or B, 2 successive A's or B's. So for example, suppose the last letter was an A. Okay, we can repeat the same argument with B as well, but if the last letter is an A, then the letter preceding it must be a B, again A, and remember length of W is at least 4, which means I surely have at least one more B. After that I don't know what happens, there could be more letters, there may not be more letters, I don't know, so I'll just put dots there. Okay, it may or may not exist. Okay, so W looks like this. So let me look at the coset of W now. Wn is, what is this? This is dot 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 B A B A N. Okay, but remember ABAN, that's the coset number 6, is the same as coset number 7, which was BABN. Okay, so by this general principle that we talked about earlier, this can therefore be written as words until B, and I will just replace the last 3 guys ABA with BAB. Okay, this only replaces the last 3 with an N. Okay, now let's stare at this. So we already observed some simplification, which is that the 2 B's occur next to each other. So that's going to cancel or give me the identity. So this becomes, so I delete the B's, and let's see what I get. I get the same 3 dots, whatever was there, the B's are gone, and now I have ABN. Okay, now look at this new expression that I have gotten. What is this? Well, this is now a word of length, the original length minus 2. right, because the two of the b's disappeared from this list. So this fellow has length equal to length of w minus 2, which is strictly smaller than the length of w. Okay. So now, since I'm doing induction on the length of w, now I'm done, because this is again of the form some word which has a's and b's. Well, you may worry a little bit about the fact that, you know, I've assumed there aren't two successive a's or b's, but you'll notice that if these dots actually existed, if say this next dot was actually a letter, that letter would be an a, okay, which would further cancel this a, or if the one before it was a b again, that would further cancel the b, and what's left is still again of the same form. Okay. So there is just a tiny little bit that you will have to do to convince yourself that the argument works without a problem, but it does. And so what we have done is, by induction the proof is done. Okay. So which implies done by induction. Okay, so what does that mean? We have shown that any coset of any word, therefore, has to coincide with one of these 6 cosets, 1 through 6, which means that our original claim was proved. Therefore, we have managed to prove, we have proved that f by n has at most 6 elements. Okay, and therefore we have proved the original thing we set out to prove, which is that and hence we have shown that the kernel of this map, the original map, was exactly the normal subgroup generated by just those 3 elements, those 3 relations. Okay. So this fact that we have shown that f modulo the normal subgroup generated by a square, b square and ab. So I'll just use this sort of angled bracket here to say normal subgroup generated by them. So we have shown this is S3. This is sometimes expressed as follows. We say S3 is the group on the generators. So we say S3 has 2 generators, A and B, and relations. So relations is the new word here, which says what's in the kernel, a square, b square and ab whole cubed. Sorry, this should be a cubed here. Okay, so there are 2 generators and 3 relations. Between them, they give you a nice presentation is the other word. This is sometimes called a presentation of S3 on 2 generators and 3 relations. Okay.